Here we are discussing one of the important point which will help us to decide changes in the energies of various molecular orbitals, which will help us to decide bond angle present in the molecule. For example, say BeH2 molecule, it is linear. Why it is so? Water molecule, angular. Why for? Even bond angle in water molecule we say 104.5 degree. So why only that angle? So such interesting facts can be explained by Walsh correlation. So let us know actually what it is. For that, let me make clear assumptions. I am assuming x-axis to our left right. Y-axis is pointing towards us and away from us. Z-axis is top down. Accordingly, px, py and pz orbitals, their orientation you will understand. As per the basis of the molecular orbital theory, we form first group orbitals from peripheral atoms. Those group orbitals interact with central atom suitable orbitals. Symmetry is very important here. For linear molecule, we are considering point group as D infinity H, and for angular that point group will be C2V. For linear molecule, bond angle variation will be 180 degree, and for angular molecule bond angle it can come up to 90 degree. Variation in bond angle may possible. If I consider H2O, one bond angle will be there. If I consider CH2, other bond angle will be there. NH2 minus, other bond angle will be there. We are focusing now on the variation in energies for molecular orbitals. In linear molecule say BH2 to angular molecule say H2O. Now focus on right side region where energies of various orbitals in linear molecule are represented. Pictorially, molecular orbitals also are shown there. Bond angle is 180 degree. Pay attention towards lowest energy orbital. That's a sigma s. Of course, it is sigma 2s, but for the sake of simplicity, I am representing it only as sigma s. Which group orbitals are combining here? Right, psi1 group with 2s orbital of central atom. If I bend the molecule, if I bring the peripheral atoms close together, then group orbitals, their lobes, those wave functions also will come close. Now already we are with positive, positive, positive interaction. That's what I am saying. Positive wave function of the one of the group orbital, positive wave function of the s orbital, and positive wave function of the other group orbital. So two positive interactions are there. If I bend the molecule, then those blue colored wave functions will come closer to each other. See here, left side portion, where you may feel that blue portions have come closer. Positive, positive or negative, negative wave functions are coming closer. Now answer for my question. If same wave functions come closer, then what will be there between them? Attraction or repulsion? Attraction. So in addition to previous attraction, between group orbitals there will be new attraction due to the bending, due to the angular structure. Therefore, as a result, energy of sigma s decreases. By red line, decrease in the energy is represented. But as the molecule becomes angular, No longer sigma and pi notations we can use. Therefore, I change that notation to 2A1, especially that notation we used for water molecule that I am giving. If you go through the video of MO diagram for water molecule, you will understand why I labeled that orbital to A1. A1 is a kind of symmetry. Even for homework, one time I asked you to generate the codings after performing various operations on all orbitals of oxygen molecule, may s orbital, px orbital, py orbital, pz orbital. From that symmetry term we devised, and that symmetry term for sigma s here is A1, and 2 is a number because below that also other A1 is there. I want to focus here about the change in the energies. So what is our conclusion? Sigma S, which was there in linear structure, becomes 2A1 in angular, and energy of 2A1 is lower than that of the sigma S. So there is a decrease in the energy. There is an increase in the stability in sigma S. Electrons in sigma S will be most happy if the structure is angular rather than linear. It is a meaning of one red curve. Now come to the other energy level, sigma X. Actually, it is generated due to sigma to px. Now pay attention towards the pictorial presentation of that orbital. I'm talking first about linear arrangement. There the orbital is px, so nodal plane is there itself in what the px. In px itself a change in the wave functions are there. Here in diagram I had not represented. I hope you are getting the point. One lobe will be positive, say left lobe is positive. Other lobe right side will be negative. Who can form sigma bonding here? Psi2 group. Out of those two groups, second group, Psi2 group will form the bond, will interact. Due to which what will happen? Left lobe will interact with positive portion of the Psi2. Right lobe will interact with negative portion of the Psi2. So here there is a change in wave function. But both where there is attraction. Where? When molecule is linear. We are attempting to bring the peripheral atoms close together. If I bend the structure, if I decrease the bond angle, I hope you will understand blue wave will come closer to orange wave. See the left side diagram. Blue and orange have come closer. I label that as 1B1. As they come closer, who came closer? Unlike wave functions came closer. What will be there between them? Repulsion, which was not there previously in linear case. Therefore, in angular molecule, sigma x orbital will increase in energy. More correctly, 1b1, which is a result of sigma x in angular structure, will be with higher in energy than sigma x. So electron existing in sigma x, what will be the feeling of the electron? Uneasy. So demand of the electron present in sigma x will be, it is better, it is linear or little change in the bond angle. If too much change, then it becomes more unhappy. So entry of electron in sigma x in angular destabilizes the molecule, decreases the stability. Here we are talking about particular energy level. So sigma x increases in energy with decrease in bond angle. Now come to the further higher level orbitals. Actually, those are the pi orbitals, non-bonding orbitals. 2py and 2pz. I represented them as y and z. When structure is linear, they are non-bonding, no suitable overlap. But as the molecule become angular, as we bend the molecule, you will understand. We said z-axis is up-down. As we bend the molecule, the bottom portion of z-axis will come closer to the peripheral atoms. So for angular molecule, how the changes will be there? Pay attention. That Z orbital had symmetry A1 as was the symmetry for 2s orbital. So group orbital having symmetry A1 will interact and that group orbital is a psi1 group orbital. Psi1 group orbital means both lobes of the group will be with same wave function. Time being say positive wave function. So as they come closer, Z orbital lower lobe, whatever its wave function is there, it will interact. We're talking about bonding orbital. So now in 3a1 orbital, the left lobe of psi1 group, middle lobe of pz orbital, and right lobe of psi1 group, all three will be with same wave function. So because of the same wave function, what do you think? Will there be attraction or repulsion? Attraction. So energy of that concerned orbital will increase or decrease? Will decrease. And see, solid decrease is there, sharp decrease is there as we change the bond angle, as we bend the molecule, as we change the molecule from linear structure to angular structure. 2p-z orbital or z orbital was non-bonding in case of linear molecule, but in case of angular molecule it decreases in energy, and that I represented as 3a1. Now come to the last orbital, that is 2py orbital or y orbital. Suitable overlap was not there, therefore it was remaining non-bonding. Now here also it remained non-bonding. Why? Because we are bending the molecule in xz plane. We are considering the molecule in xz plane. So y orbital in linear case also will remain perpendicular and in angular case also will remain perpendicular. There will not be the proper overlap in linear case as well as in the angular case. So there is a no change in the energy for y orbital. This energy variation for general molecules. In particularly, if I have to talk about water molecule, then see here in between blue colored line is there. That indicates the energetics for water molecule. If you say other molecule NH2 minus, energetics will be different. CH2 energetics will be different. But this Walsh correlation will help us to explain that. So how overlap takes place, to how much extent it takes place, what is electronegativity of central atom, what is the bond length. Many factors are there, those decide the bond angle. Now let us discuss in detail electronic distribution for both H2O and BeH2 and correlate them in order to have better cognizance of Walsh correlation diagram. Pay attention. For linear molecule, I considered example of BeH2 and a distributed electrons. Only 4 electrons are there in the representative orbitals. 2 electrons in sigma s and 2 electrons in sigma x. No electrons are there in pi orbitals. If this molecule would have been angular, the electrons in sigma s will be happy because their energy is decreasing, while electrons in sigma x will be unhappy. Why? Because their energy is increasing. And for non-bonding, electrons are not there, so there is no question. So in totality, if you observe, decrease of sigma s is to low extent compared to increase in sigma x. So unhappiness will be more relative to happiness. Stability will be less. Therefore, BeH2 prefers linear arrangement. That's the most suitable arrangement energetically. Now come to the water molecule. Blue line is in between. Their electrons also are represented by black color. In each orbital, in each level, two electrons are there. First is 2a1, next one is 1b1, next one is 3a1, and last one is 1b2. If this water molecule would have been linear, then what will happen? Electron in sigma s will be unhappy because in band structure, in angular structure, it is stable. Okay, let us talk about other. Electron in 1b1, which will turn to sigma x, will be happy because its energy will decrease. Electron in 3a1 will be unhappy because its energy will increase and that molecular orbital will turn to non-bonding Z orbital. About non-bonding, that's a 1b2, no more point to discuss. In totality, if you observe, increase in energy at 2a1 and at 3a1 is very more compared to decrease in energy. So due to which what will be the preference for water molecule? Angular structure. If linear, it will be not more stable. So angle between the bonds is observed in order to give the stability to the molecule. So linear arrangement is a not suitable arrangement for water molecule. Now question you will be with, why in between only? Why the bond angle in water molecule is 104 degree or 104.5 degree? Why not it is 90 degree? Pay attention. In case of angular molecule, the sigma s orbital means that I am saying as 2a1 orbital. As angle is small, as angle is less, most stable. So electrons in 2a1 will welcome to find 90 degree as a bond angle. So 2a1 is in favor of 90 degree bond angle. What about 3a1? 3a1 also is in favor of 90 degree bond angle because energy is decreasing. What about 1b1? It is not in favor of 90 degree bond angle because its energy is increasing. But if you see favor of 2a1 and 3a1 is very huge, very large, structure should be 90 degree. So in H2O, bond angle should be 90 degree. But it is not. What is the reason? See, molecular orbital formation depends on symmetry, depends on energy. By the way, it depends upon overlap. What are we doing? We are bending those peripheral atoms in such a way angle is 90 degree. Due to which what happen? Certainly interaction with PZ orbital will increase, but there will not be any interaction with px orbital, which was in linear case strong interaction. Ideally, if we bend the molecule further lesser than 90 degree, px orbital will not interact. Therefore, only up to 90 degree variation is represented. But reality may be different. Size of the central atom, electronegativity of the central atom, bond length, these all factors matter. In case of water molecule, the electronegativity of oxygen, size of the oxygen, bond length is in such a way that 104.5 degree is a most stable bond angle, or 104.5 degree angular separation is most stable. If we decrease bond angle further, then what may possible? Px orbital may not overlap. And if it doesn't overlap, then its energy will suddenly shoot high, very high, which was poorly, slowly increasing. No, it will be the dominating molecule, will be the extremely unstable. And if the bond angle is higher than the 104.5 degree, then stability point of view, it is less stable. Reason, chance is there for 2a1 orbital to decrease, 3a1 orbital to decrease. So where there is a maximum stability, that bond angle will be chosen by the molecule, and in case of water molecule 104.5 degree is a most suitable bond angle from energetics point of view, from Walsh correlation diagram point of view, hence the observation. If I have to talk in addition, the NH2 minus, their central atom is nitrogen. The molecular arrangement is similar like water. Because nitrogen is less electronegative than oxygen, the bond length is different. And because of difference in bond length, we can't bend the NH2 minus further. Its bond angle is higher. So I hope you are getting this point. How electronegativity, how size of the central atom, how overlap or how bond length matters here. Now question as a homework. Why is water molecule angular? I had given explanation in the video. Only you have to put those in proper words and write the answer in comment box. Short answer, please do write. I am waiting for your answer. Now here our unit number 1 completes.